Welcome back, my dudes, my fellow colleagues. This is 202, happy number. This one's not too bad, my dudes. But if you're struggling, it might be because you don't know if you might be missing some key mathematical intuitions. That's okay. We're going to cover that here. So the question is, write an algorithm to determine if a number n is happy. And we're going to determine if a number n is happy based on some criteria that they define here. Happy number is a number defined by the following process. Starting with any positive integer, replace the number by the sum of the squares of its digits. Okay, and just to pause here, we can see that we have n is equal to 19. So 1 squared plus 9 squared is equal to 82. And that becomes the value. Repeat the process until the number equals 1, where it will stay, or it loops endlessly in a cycle which does not include 1. So, going from the previous part we just talked about, 1 squared plus 9 squared is equal to 82, so the number is 82 now. 8 squared plus 2 squared is equal to 68. So the number is 68 now. 6 squared plus 8 squared is equal to 100. The square of all these numbers, because 1 squared is 1, and 0 to the second power is 0, and so on. And so you get 1. 1 is a happy number. 2 is not a happy number because 2 squared is equal to 4. 4 squared is equal to 16. You go on and keep going on and keep going on. And that one will eventually loop forever. So, key intuitions here. Starting with any positive number, replace the number by the sum of the squares of its digits. So, from the first part, we know, right, that there are a few things we have to do. We know that we can kind of run with a naive solution here. And we'll just, you can just loop, right? While, let's just say, n does not equal -1, linearly, let's just say, loop while n does not equal 1, right? Linearly summate squares, update n, and if we, while n does not equal -1, right? If we make it out of this loop, then we'll know that we can just return true, right? Because it means that we stopped because n was equal to 1, right? And in here, what you can do is what you realize is kind of the second caveat of the problem, right? Repeat the process until the number equals 1, where it will stay, or it loops endlessly in a cycle which does not include 1, right? So how do we know if we are in a cycle? So let's flesh this out, right? So if we want to know how we're in a cycle, right, how could we do that? Well, we could keep a dictionary, right? And so for each sum that we create, we're just going to throw it in the dictionary. And usually with the dictionary, you have to map some key to some value, right? But in this case, usually you map, like, if you're, doing an anagram kind of problem, you can do letter to occurrences, right? For this one, we're only going to use a dictionary strictly for bookkeeping purposes. We just want to know if something's in the dictionary or not, right? So the value that we're mapping it to doesn't really matter. It just matters that the key is in the dictionary. So keep a dictionary, right? From here, we'll just do, it'll be from the sum, which is the key, or I'll just do like this, key, which is the sum, to value, which is just going to be, whether it exists or not. But this, we're not really going to set it to anything other than 1. Just because it doesn't really matter what we set it to, right? We just want to know that it's in the dictionary, right? So we have this dictionary, right? And what we can do is, once we linearly summate the squares, right, we're going to get a sum. And we're going to update n with the sum, right? Because as we said, we start at 19, linearly summate the individual components of the number, we get 82, linearly summate the squares of the components, get 68, and so on, right? So you have to update n with the sum after each operation. Hopefully you end up at 1, right? So if we update n with the sum, right, then we'll just check in the dictionary. Hey, dict, did we see this number before? If we did, we're in a loop. Yikers. If not, if we didn't see it before, right, add it to the dict, right? Because if we haven't seen it before, let's add it into the dictionary so next time we see it, we don't do it again. I mean, we will quit because we'll know we're in a loop, right? So this is kind of the scaffolding of the entire solution to the problem, right? So let's flesh this out with actual code. So what we'll do, we'll create a dictionary, we'll call it scene. And I'm just going to comment out our stuff here so we can actually, and I'll write the code beneath each part so it makes more sense. So a loop while n does not equal 1, right? Well, n does not equal 1 because we want to stop if we can reach 1. And if we only stop when we reach 1, then we have to have some way to break out if you were in a loop, right? So this is where the dictionary part comes in. So now we need to linearly summate the squares, right? So how do we summate the squares? So we're obviously going to need another loop, right? It's unavoidable because we have to loop over the individual components of the number to calculate the value, right? It's a little bit unavoidable. You could probably do some bit stuff here, but we're not going to do that. We're just going to keep it simple. And so what you can do here, I'm going to show you a couple cool tricks that you can actually take to other problems, which are going to be pretty useful. So the second thing we're going to do is we're going to do for blank in range of turning, we're going to turn the number into a string, right? So we're going to turn the number into a string, and then we're going to loop for each letter in the number, right? The reason I'm putting a underscore here is because we don't really care what the value is. We just want to loop that number of times, right? So what's cool here is the reason we're doing it this way, right, is I want to show you some things you can do. So I'm going to open up Spotlight here, and what you can see is that let's just say we have the number 1001, right? If you need, actually, let me not use Spotlight. Actually, okay, if you have the number 1001, right, what you can do is you can do mod 10, right? You actually get the last number. You actually get the last number. So if you do 1001 mod 10, what you get is the last number, which is pretty cool. So if you had like, just to make this a little more sense, if you do 1005 mod 10, you get 5, which is the last number in this number, or the first number, if you're talking it from the powers stance. So if you do 1005, but divided by 10, what you do is you kind of move the decimal place over, and what you get is 100.5. And if you were to turn this into an integer, what you get is 100. So with these two methods, instead of having to, what you could do is linearly, you could iterate over the string, right? If you could turn a number into a string, iterate over the string, and then cast that number back to an integer, square it, and you can add it to the sum, right? But that's a little too much, right? And what you get from here is actually simpler and faster ways to do this. So we need to linearly summate the individual components of the number, right? Linearly summate the squares of the individual components of the number, right? So we can use the mod trick here. So we're just going to say num. Yeah, we're just going to say num is going to be equal to n mod 10, right? And then we'll have to keep track of sum. Sum is going to be equal to 0 for now, and then we need to so we want to linearly summate the squares, right? And so what we can do here, which is kind of cool, is we can do num. We can do n is going to be equal to n divided by 10. And so this way we're kind of sliding the number down, right? Which is kind of cool. And so this way we'll get all the values that we need. And then from here we can do sum plus equal num exponentiate 2. And so just to remove all this stuff here. So we chopped the number off at the end. We're modifying n, right, so that we can kind of keep popping numbers off the front of it, and then we'll kind of get to the end of it. And then I'm just going to do int here, just so that we go from 100.5 or something like that to 100. And then the next time we do it, we'll get 10, 1, and so on and so forth, right? Boom. And then from here, like we said, we have to update n with the sum, right? Because when we do 1 squared plus 9 squared equals 82, perfect, we have the next number. Now we're working with 82, right? So that's something we also have to do. So I said we have to update n with the sum. And we're going to do that here. But we have to do it outside of the loop, right? Because we don't want to update it each time, even though it doesn't really matter. And so what we're going to do is we're going to say n is going to equal to sum, right? We said, how do we know if we're in a cycle? We have to check in the dictionary, right? So we're going to say if sum in scene, then we're going to return false. We've seen this. We're in a loop. Get me out. Else, we're going to add it to the dictionary. Scene sub num is going to be equal to 1. And the last thing we have to do, I believe, oh no, we should be good here. And so I'm just going to remove all these extra comments. And so we should be able to give this a run. We have to slide all this up. First time doing this problem, by the way. Oops. And we want to do this, the length of the string. That's my bad. And boom. So we have 32 milliseconds, fast and 80%, 75%. So that's pretty good, right? So what I added here with length, we just want to, iterate over the length of the string of the number. So we have to cast it to a string first, so it actually can be broken up. Then we take the length of that string, and then we'll iterate over it. So what's the time complexity of this, right? So another important thing to note, right, is that there's kind of a logarithmic nature to this problem. So just to give you a closer look at what I mean, so we have to linearly summate the squares of the individual components of the number, right? But if you have a number like 83, if you take the log of 83, what you get is 1.91. If you seal that, then you get 2. And you can kind of keep going with this. If we take 40, if we do the log of 4,123, you get 3.6. Log, you get 3.62. You seal that, and you get 4. So what you get is you can get the length of a number by using the log, right? And so there's an inherent logarithmic nature to linearly summating the individual components. And so the problem in hand has a very close nature to linearly summating the squares of the individual components. And so our time complexity is going to be closely related to that. If you take this one right here, to get 82, we have to sum 2 individual objects. And to do that, we can get that number that the amount of operations we need to do by taking the log of it. To do 82, we have to do the log of that, which is 2 operations. 68, log of that. Log of 100 is 3 operations to get 1. So we're going to have log of n plus log of n plus log of n plus log of n plus log of n. And then you can summarize that to basically just be log of n, which is the time complexity. And since we're storing a value each time, because we have to, well, most times, right? We're storing a value in the dictionary, the space complexity is also going to be log of n, because it's also to hide in very close nature to that as well. So we have log of n runtime and log of n space complexity. This is happy number.